Ever wondered if ancient civilizations knew something we don't? Prepare to have your mind blown as we dive into 5 mysteries that baffle modern science. First up, Roman concrete versus modern mixes. Why theirs lasts 2,000 years while ours cracks like a bad joke after decades. Then, the Baghdad battery. Ancient clay pot that might generate electricity. Shocking discovery from 2 millennia ago. Next, Mayans' uncanny eclipse predictions without telescopes. Cosmic calculators charting heavens with incredible precision. And who could forget Greek fire? Mysterious substance burning on water. Ultimate unquenchable campfire fail. Finally, the Egyptian pyramids. Still standing tall, ancient engineering secrets a puzzle we can't replicate today. But hold on before jumping to alien conclusions. It's human genius with forgotten know-how. Ancestors were far more advanced than we give credit. Join us for the full compilation as we uncover astonishing truths behind these enigmas. You won't want to miss it. SciCuriousID presents. Picture this. Ancient structures like the Pantheon in Rome, completed around 128 Anno Domini, standing strong and majestic for nearly 2,000 years, defying relentless time, harsh weather, earthquakes, and relentless elements. Now, contrast that incredible endurance with our modern concrete buildings and bridges, which often start crumbling, cracking, and failing within just 30 to 50 years. This isn't nostalgia. It's a paradox of modern engineering. How did ancient Rome build concrete that outlasts our most advanced materials today?
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
Concrete is the most widely used material on Earth today, with a staggering over 30 billion tons produced every single year, fueling everything from skyscrapers to sidewalks. Yet, this ubiquitous powerhouse is also a massive CO2 emitter during production, and despite its dominance, it cracks and degrades like my ambitious New Year's resolutions after the first week of January. At the heart of modern concrete is Portland cement, a fine powder made by heating limestone and clay, then grinding it with gypsum. When mixed with water, it forms a calcium silicate hydrate gel, or CSH, that hardens into a solid mess. However, once this CSH gel fully sets, it becomes largely chemically inactive and inert, so any microcracks that develop from stress, shrinkage, or environmental exposure just keep propagating and widening over time, compromising the entire structure's integrity. The clever Romans crafted their revolutionary opus cementitium using a smart recipe of lime, volcanic ash called pozzolana sourced from places like Pozzuoli near Naples, and often seawater for mixing, yes. They intentionally used ocean water, giving their concrete that extra salty attitude. Roman architect Vitruvius even specified precise ratios, like 1:3 lime to pozzolana for general construction and 1:2 for underwater work, blending it with aggregates like rock, tiles, and rubble for unmatched strength. The true magic ingredient was pozzolana, packed with reactive silica and alumina that kick off a pozzolanic reaction with calcium hydroxide from the lime, continuously forming fresh calcium silicate hydrate and aluminate compounds over centuries, keeping their concrete chemically alive and evolving like zombie concrete that just won't die. This ongoing reaction fills voids, densifies the matrix, and builds strength progressively, turning their builds into time-defying powerhouses. Cutting-edge research has unveiled Roman concrete's astonishing self-healing superpowers. When water seeps into a crack, it activates small lime clasts, tiny quicklime fragments from their hot mixing technique, triggering a reaction that creates a calcium-saturated solution, which recrystallizes into calcium carbonate crystals, sealing the fissure shut just like frost creeping over a window pane. No ancient myths here, just pure, brilliant chemistry in action that keeps structures watertight and robust. Especially when mixed with seawater, this process sparked the growth of rare aluminous tobermorite and philipsite crystals, which are aluminum-rich and silica-poor compared to natural versions, interlocking and densifying the concrete matrix to make it even stronger with age. These unique crystals turn time from a destructive foe into a powerful ally, enhancing durability against fractures, corrosion, and marine assaults over millennia. So why did we ditch this superior Roman recipe? The 19th century industrial boom demanded lightning-fast construction, and Portland cement, invented around 1824, delivered quick-setting convenience ideal for rapid urbanization, but sacrificed that legendary long-term durability for short-term speed. Did you know the Romans poured this magic mix into wonders like the Pantheon, whose massive unreinforced dome, the largest in the world, still stands pristine after nearly 2 millennia, using lighter tuff and pumice aggregates at the top to ease stress? Meanwhile, many modern bridges and dams struggle and decay after mere decades, mind officially blown. Modern reinforced concrete battles nasty issues like steel rebar corrosion from water, salt, and air infiltration, plus sulfate attacks, lime leaching, and alkali aggregate reactions that crack and weaken it over time. But excitingly, scientists are now reviving Roman techniques with pozzolanic additives and hot mixing for self-healing, lower CO2 emissions, and vastly improved longevity in our builds. By rediscovering this ancient wisdom from structures like still-flowing Roman aqueducts and the seaworthy harbor of Caesarea Maritima, we can forge a sustainable, ultra-durable future for construction. Hit like and subscribe for more hidden gems of science and history.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.
Long before Tesla, long before Edison, an ancient object discovered near Baghdad sparked one of archaeology's most controversial questions. Did people 2,000 years ago understand electricity, or are we projecting modern ideas onto the past? This is the story of the so-called Baghdad Battery and why scientists are still divided.
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
In the 1930s, archaeologists excavating near modern-day Baghdad uncovered a small ceramic jar. Inside it were 3 key components: a copper cylinder, an iron rod, and traces of an acidic residue. The artifact dates roughly to the Parthian period, between the 1st century BCE and 3rd century CE. At first glance, it looks unremarkable. But to a modern chemist, the configuration raises eyebrows. A battery at its core is simple. You need 2 different metals and an electrolyte, a liquid that allows ions to move. Copper and iron have different electrochemical potentials. Place them in an acidic solution like vinegar or wine, and a galvanic reaction occurs. Electrons flow. Electric current is generated. In laboratory tests, replicas of the Baghdad battery can produce around 1 volt of electricity. 1 volt sounds impressive until you consider current. The replicas produce extremely low amperage, not enough to power devices, not enough to store energy efficiently. This is crucial. Electricity isn't just about voltage, it's about usable power. So if this was a battery, it wasn't powering lamps, motors, or ancient gadgets. One popular theory suggests electroplating. Electroplating uses electricity to coat objects with thin layers of metal, like gold. In theory, a weak current could deposit metal ions. But here's the problem: no wires were found. No plating babs. No clear electroplated artifacts conclusively linked to this device. From a scientific standpoint, the archaeological evidence is incomplete. Another idea suggests medical therapy or religious rituals, using mild shocks to impress or heal. But again, there is no textual evidence, no medical writings, no ritual descriptions involving electric sensation. Ancient civilizations documented rituals obsessively. If electricity played a role, we would expect some record. We find none. Many archaeologists argue the simplest explanation: it wasn't a battery at all. Similar jars were used to store scrolls, sacred liquids, or ritual objects. The acidic residue could come from organic materials. The metal components may have had structural or symbolic purposes. This interpretation requires no lost technology, no forgotten science. Yes, replicas can generate electricity, but generating electricity accidentally is not the same as understanding electricity intentionally. Nature itself creates galvanic reactions constantly in soils, in water, even inside living organisms. The key scientific question is not could it produce electricity, but was it designed for that purpose? Extraordinary claims require extraordinary evidence. The Baghdad battery reminds us how science works. We test ideas. We compare explanations. We favor interpretations with the fewest assumptions. Right now, the electrical hypothesis remains possible, but unproven. The object survives without context. No manuals, no wiring, no corroborating artifacts. And when evidence is incomplete, mystery fills the gap. Not because ancient people were incapable, but because our data is. The Baghdad battery doesn't prove ancient electricity, but it does prove something just as powerful. Human curiosity, experimentation, and ingenuity have deep roots. Sometimes the real wonder isn't what we imagine the past could do, but how carefully science teaches us to separate fact from fascination. Subscribe for more mysteries where science meets history without the myths.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.
Predicting solar eclipses remains a monumental challenge even today. With our advanced supercomputers, satellite networks, and precise orbital models that crunch vast amounts of data to forecast these events down to the exact second. Yet, astonishingly, over 1,000 years ago, the ancient Maya civilization in Mesoamerica accomplished this incredible feat without telescopes, satellites, or even a single sheet of modern paper. They relied solely on patient naked-eye observations and ingenious pattern recognition. How did the Maya, armed with their profound and intricate knowledge of the cosmos, achieve such a mind-blowing accomplishment that still impresses modern astronomers? Get ready to buckle up and hold on tight, because we're diving headfirst into a captivating journey through the wonders of ancient astronomy and the Maya's stellar genius.
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
The Maya weren't some mystics peering into crystal balls or consulting oracles. No, they were the ultimate data scientists and meticulous skywatchers of their era, with priests and astronomers dedicating entire lifetimes, spanning centuries, to carefully observing and recording the precise movements of the sun, moon, planets, and stars right from the lofty summits of their massive, towering pyramids that pierce the jungle canopy. Picture their notebooks, not today's sleek laptops with infinite storage and AI assistance, but fragile bark paper codices, laboriously inscribed by hand with thousands of glyphs and numerical records, and let's be real, definitely no autocorrect to fix those intricate hieroglyphs when a quill slipped during a late-night stargazing session under the stars. To truly appreciate their genius, let's quickly recap the basic science of eclipses that they mastered through pure observation. A solar eclipse occurs when the moon glides directly between the sun and Earth, casting its umbral shadow across our planet's surface for those magical moments of daytime darkness. A lunar eclipse, on the other hand, happens when Earth positions itself between the sun and moon, with our planet's shadow engulfing the moon in a coppery glow. The crucial factor is not just perfect alignment, but also the moon's orbital plane, which tilts about 5 degrees relative to Earth's orbit around the sun, creating specific nodes where crossings enable eclipses. The Maya didn't grasp modern orbital mechanics or gravity, but they excelled at detecting repeating patterns in the sky's dance, because as any scientist knows, true discovery often begins with that excited exclamation, "Hey, that happens again. Let's track it." At the heart of their predictive prowess was the Dresden Codex, one of the miraculously surviving 4 Mayan books that escaped the fiery destruction by Spanish conquistadors, serving as their ultimate cheat sheet. Packed with detailed eclipse tables that meticulously charted the cycles and periodicities of both the moon and sun over vast spans of time. This treasure trove wasn't focused on unraveling the underlying why of eclipses through physics, but laser-targeted on the practical when. Pinpointing recurrence intervals with such reliability that it allowed them to anticipate events months or even years ahead, which, if you think about it, is brilliantly pragmatic when you're charting the heavens without a supercomputer or even a calculator in sight. Through relentless observation, the Maya pinpointed that a synodic month, the interval from one new moon to the next, clocks in at approximately 29.5 days, and they astutely identified eclipse seasons recurring roughly every 177 days, a period that neatly aligns with about 6 synodic months. By cleverly stacking these cycles atop one another, along with other harmonic numerical patterns like multiples of 13 and 20 from their vigesimal system, they constructed reliable forecasts for when eclipses were most probable. It was all observational mathematics at its finest, no need for Newton's laws or Kepler's ellipses, just extraordinary patience, sharp eyes, and an intuitive feel for the cosmic rhythm pulsing through the night sky. Of course, their predictions weren't laser precise to the exact minute or path like today's GPS-guided models, but instead offered practical windows of opportunity spanning days, which was still leaps and bounds ahead of anything achieved in Europe before the era of Isaac Newton and his revolutionary calculus. The sheer precision they attained purely through centuries of dedicated skywatching and data logging underscores their unwavering commitment to astronomy, proving that sometimes the simplest tools, eyes, patience, and patterns, can unlock the universe's deepest secrets. Here's a delightful pattern-interrupting fun twist to blow your mind. The Mayas' eclipse mathematics was so robust and finely tuned that many of their calculated intervals align uncannily well with elements of our modern Gregorian calendar systems, as if these ancient stargazers were pros setting up celestial appointments that echo perfectly even today, centuries later. For the Maya, solar and lunar eclipses transcended mere astronomy. They were potent omens believed to imperil kings, crops, and the very fabric of social order. So mastering their prediction bestowed immense ritual power and societal stability upon their priestly class. This saga reminds us that raw data and tireless observation often outshine lofty abstract theories, and the Mayas' patient vigil over the heavens truly conquered the cosmos' enigmas. If you loved this dive into ancient scientific wonders, give this video a like and subscribe for more thrilling tales of history's hidden geniuses.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.
Imagine a weapon so terrifying it didn't just burn ships, it burned on the sea itself, deployed by the Byzantine Empire in the early Middle Ages. This liquid fire, known as Greek fire, appeared to violate basic physics by continuing to burn even when water was poured on it. This liquid fire, called Greek fire, appeared to violate basic physics, as it could not be extinguished by water no matter how much was thrown at it. Historical accounts describe it as an unquenchable inferno that spread relentlessly across the waves. Despite centuries of research by scientists and historians, its true science remains lost to time, making it one of history's most intriguing technological mysteries. Even today, no one has fully replicated its exact effects.
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
Greek fire emerged in the 7th century CE during a dangerous period for the Byzantine Empire, which faced repeated naval sieges, especially from Arab fleets. This weapon became crucial as the empire struggled to defend its shores. It was developed by engineer Callinicus, a Syrian who fled to Constantinople, creating a strategic equalizer that helped save the empire from collapse during those desperate times. His invention turned the tide in many battles. Greek fire was not a single device, but a complex system involving a flammable liquid, pressurized pumps for projection, and bronze siphons mounted on the decks of Byzantine ships. This intricate setup allowed for precise and devastating deployment. Contemporary accounts from various sources consistently describe three key properties. It ignited easily with a spark, clung stubbornly to surfaces like wood and flesh, and continued burning fiercely even on water. These traits made it uniquely horrifying. From a scientific perspective, fire burning on water is possible, but requires very specific conditions to overcome water's natural ability to cool and smother flames. Understanding this helps explain why Greek fire was so extraordinary. The substance had to be less dense than water so it could float, spread out rapidly across the surface, and sustain its own combustion without relying on external oxygen sources, ruling out ordinary fuels like wood or oil alone. This combination was key to its persistence. Most modern reconstructions propose a petroleum-based mixture, likely including naphtha for high flammability, sulfur to lower the ignition temperature, and resins or pitch to make it sticky and adhesive. These ingredients were readily available in the Eastern Mediterranean region. These substances were well known in the Eastern Mediterranean, and crucially, petroleum floats on water due to its lower density, allowing the flames to spread across the sea surface like a fiery blanket. This property amplified its destructive reach. Some historians suggest quicklime or calcium oxide as a key component, since it reacts violently with water to release intense heat and steam, potentially igniting nearby oils or fuels. This exothermic reaction would have added to the terror. However, modern chemical analysis indicates that quicklime was likely just a trigger mechanism, providing initial ignition, rather than the primary fuel, which needed to burn longer and more steadily. This distinction clarifies its role in the mixture. The true genius of Greek fire may lie not just in its chemistry, but in its sophisticated delivery systems that ensured reliable projection over distances. These innovations elevated it beyond a mere incendiary. Byzantine engineers created the world's first naval flamethrowers using pressurized pumps to force the liquid through tubes and heated reservoirs to keep it fluid and ready to ignite. This allowed sailors to spray fire streams accurately in battle. This unprecedented combination of advanced chemistry and mechanical engineering set Greek fire apart, integrating fluid dynamics, metallurgy, and combustion science in a way never seen before its time. It was a pinnacle of medieval tech. Greek fire didn't just destroy ships physically, it shattered the morale of enemy crews as water, their only supposed defense, made the flames spread faster, and traditional methods like sand or vinegar utterly failed. Panic ensued on the decks. Enemy crews, witnessing the horror, described it poetically as liquid lightning or fire from heaven, underscoring its profound psychological impact that often won battles before swords were drawn. It was terror incarnate. Now for a fun fact to surprise you. Did you know that the Byzantines sometimes used Greek fire in handheld devices, like clay grenades filled with the mixture, for devastating land warfare too, lobbing firebombs over walls? This versatility made it even more formidable. Greek fire was a closely guarded state secret, with knowledge compartmentalized among trusted artisans so no single person knew the full recipe, and it was never fully documented in writing. This secrecy ensured its exclusivity. When the Byzantine Empire finally collapsed in 1453, the intricate knowledge infrastructure, workshops, experts, and supply chains vanished with it, following a common pattern seen in other lost technologies throughout history. Empires fall, secrets die. Modern chemists can indeed create substances that burn on water using similar ingredients, but none fully replicate the historical accounts of its long range, strong adhesion to targets, and prolonged persistence in combat conditions. The exact balance eludes us. This gap suggests Greek fire was not merely a single compound, but a carefully tuned system, fine-tuned to local climate variations, available materials, and specific naval tactics of the era. It was holistic engineering. Greek fire reminds us that groundbreaking science doesn't always live in textbooks or public records. It can thrive as practical craft, handed-down expertise, and closely guarded trade secrets among skilled practitioners. Theory meets hands-on mastery. Sometimes profound knowledge isn't lost because it was mystical or supernatural, but simply because it was never systematically written down, relying instead on oral tradition and apprenticeship. documentation was not always prioritized. And when empires crumble and traditions break, even the mightiest fire can vanish silently into the pages of history, leaving only echoes in ancient texts. Its flame endures only in legend. If you found this journey into the lost science of ancient technology as fascinating as I did, please subscribe for more deep dives where history meets hard science, stripping away the myths to reveal the real ingenuity.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.
Built over 4,500 years ago, without steel, cement, cranes, or electricity, the Egyptian pyramids are still standing. They're not leaning, not collapsing, and not repaired every few decades. The real question isn't how impressive they look, but why they still function as structures.
Behind every question lies discovery. I'm Seluna, and this is SciCurious, where we uncover the science shaping our world.
When we talk about the pyramids, we're usually referring to the Great Pyramid of Giza. It originally stood at 146.6 meters, built from about 2.3 million stone blocks, weighing over 6 million tons. This wasn't primitive construction, it was large-scale structural engineering. The Great Pyramid is aligned to true north with an astonishing error of only about 0.05 degrees, even by modern standards. Without compasses or GPS, Egyptian surveyors likely used stellar alignment and shadow-based solar geometry. This was applied geodesy, performed with extreme methodological discipline. The pyramid shape isn't just symbolic, it's structural. Every stone is loaded almost entirely in compression, which stone handles exceptionally well. Unlike modern buildings that rely on beams and tension, the pyramid channels gravity straight down into the bedrock, making them naturally earthquake-resistant. Inside, engineering becomes even more sophisticated. Above the king's chamber are relieving chambers, stacked granite slabs redirecting enormous loads away from the chamber ceiling. This load path engineering, similar to modern bridges and tunnels, was executed in stone 4,500 years ago. The pyramids used two primary materials: locally sourced limestone, excellent in compression, and extremely hard granite, used strategically in high-stress zones. Limestone slowly hardens over time through recrystallization, while granite is chemically stable and resists weathering. This wasn't random, it was functional material optimization. Experiments show that pouring water on desert sand reduces friction by up to 50%, turning loose sand into a temporary solid track. With sleds, ropes, and coordinated labor, multi-ton blocks became manageable. No anti-gravity, no lost machines, just applied physics. The pyramids survive not because time spared them, but because their environment helps. Egypt's arid climate limits biological decay, freeze-thaw cycles, and chemical weathering. But climate alone isn't enough. Poorly designed stone structures nearby did collapse. Design truly mattered. Modern buildings prioritize speed, cost, and flexibility, relying on materials like steel and concrete, which are vulnerable to corrosion and fatigue. The pyramids, however, prioritized mass, simplicity, and permanence. No moving parts, no chemical reactions waiting to fail. Different goals produce vastly different lifespans. Here's a fun fact. Did you know the Great Pyramid was the tallest man-made structure in the world for over 3,800 years, until Lincoln Cathedral was completed in 1311 AD? The Egyptians didn't know Newton's laws or calculate stress tensors. Yet, they understood empirical engineering through centuries of iteration. This was science before equations, a deep understanding of what works, what fails, and why. The pyramids are still standing not because they were mysterious, but because they were honest structures. They respected gravity and worked within material limits. Built to endure, not to impress quarterly reports, the pyramids are engineering lessons we still haven't fully learned. If you found this journey through ancient engineering fascinating, Please like this video and subscribe for more science-backed explanations of history's greatest marvels.
And so, our journey through the echoes of the past concludes. From concrete that heals itself to whispers of ancient electricity, we've delved into the profound mysteries of civilizations long gone. These weren't just tales, they were glimpses into minds that shaped our world, challenging our understanding of what was possible millennia ago. We've seen how Roman engineering defied time, with structures standing strong for 2 millennia thanks to self-healing concrete. Then, the enigmatic Baghdad battery sparked debate, hinting at forgotten electrical knowledge. And Mayan astronomers mapped the cosmos with astonishing precision. The devastating power of Greek fire showcased ancient warfare's ingenuity, while the monumental genius behind the pyramids continues to baffle modern engineers. These weren't just mysteries, they were testaments to human ingenuity, resilience, and an insatiable quest for knowledge. It makes you wonder, what other forgotten knowledge, what other incredible discoveries are still waiting to be rediscovered?